So as we've seen before, the planets that are closest to the sun orbit the fastest. They have the smallest orbital period. And the reason that this is connected to Newton's laws is that it's the force that creates the acceleration that causes planets to move at a given speed. All right, so when you have more force near the sun, then you have a higher speed. So it's a very simple connection when you think about it. And it was actually possible for Newton to prove Kepler's laws by using his new law of universal gravitation. So that's pretty satisfying when you can actually prove a law of nature mathematically. So I want to apply Newton's laws and Kepler's laws briefly and give you just a preview of the homework for this week. So if we come back to the idea of Kepler's third law, which was that the period squared scales as the semi-major axis cubed, that's not actually totally correct. Kepler's third law actually states that the period squared is equal to the total mass of both objects times the semi-major axis squared. But remember, we just said that the mass of the planets are pretty much negligible compared to the mass of the sun. And so for all practical purposes, this equation, you can basically say that the mass of the planet doesn't count at all. And so we get p squared is equal to the mass times the semi-major axis squared. And when we use our standard units of the period in years, the semi-major axis in AU, and the mass of the sun in solar masses, then all of this simplifies to simply working out to p squared equals a cubed directly. But the fact that this mass of the star is a part of the equation lets us do something interesting, right? If we look at wanting to calculate the mass of an unknown star, a star with unknown mass, we can use its orbital characteristics of its planets to measure that mass. We can also do something else that's interesting related to exoplanets. So to warm you up, exoplanets are planets that are around stars that are not the sun. So lots of stars have planets, and these are a few of them that are thought to be in the habitable zone of their stars. They're all named after their star. So Kepler 442b and all of those stars are named after, all the planets are named after the star. And if you take off the letter, then you'll get back the name of the star. So Kepler 442b orbits around the star Kepler 442. The reason these are all called Kepler is because there's a space telescope called Kepler, and it's the one that's looking for exoplanets. Okay, so I have a question, which is, how would we know if any of these exoplanets were habitable? And just to get you started, let's define the habitable zone as the place where liquid water can exist on the surface of a planet. So given that, what affects, that shouldn't say the distance, I think I'm giving it away, but what affects whether or not a planet is habitable? For habitability, we might want some water on the planet, air, maybe oxygen if we want to live there, for sure, oxygen, a stable temperature, a temperature that's good for liquid water specifically, and something that ensures that your planet isn't completely frozen, but also that it's not too hot for there to be necessary resources like water or other nutrient sources that could be, burned off or otherwise inaccessible if your planet's too hot or too cold. All right, so that's exactly right. And so the connection to distance is that connection to temperature. And different stars, they actually have different surface temperatures based on the type of star they are. So some stars are very hot and bright, other stars are dim and cool. And just in general, if you have a hot star, you need to be farther away from it in order not to get baked, right? In order for the water not to basically evaporate completely or get completely burned off and lose your entire atmosphere. But you also need to be close enough to your star so that you do have that liquid water. So this top one is a hot star. So a more massive star burns hot. And so this massive star, you have to be farther from the star compared to our one solar mass star. But there's a wider range of habitability. So this yellow region is supposed to be the entire habitable zone. So if you had a planet here toward the inside of that zone, that's habitable. If you have a planet out toward the outside of the zone, still habitable. All right, so the zone is wider there's a narrower acceptable range when you have a cool star, but you can be a lot closer to the star. So I just want to point out that when we're looking at exoplanets, we can't measure everything about their orbits. They're actually too far away in general for us to measure directly their orbital distance using a telescope, because they're just not distinguishable for the most part from their stars. They're not bright. You can only see the star for the most part. So we can't really measure their orbital distances. But by using the amount of time it takes for the planet to obscure the star each time that it makes an orbit around its sun, then we can see, you know, the star goes dim when the planet is in front of the star from our perspective. And so if we count, you know, how often it takes for that dimming to occur, we can get its orbital period. So we can measure P, the orbital period. And if we do this, we can get the mass of the star and also its orbital distance. So in your homework, what I'm going to do is give you this equation, P squared is n times a cubed. And I'm going to ask you to apply that equation to figure out if various exoplanets are within their star's habitable zone based on their orbital periods and the mass and temperature of their star. So hopefully this will be a fun way to apply what we've been learning about Kepler's laws